Hi, I'm Jonathan Aldrich. Let's talk about type checking. Let's consider some of the key aspects of type checking. The first aspect is type compatibility. When can a value of type A be used in a context that expects some other type B? This is very similar to our first definition of subtyping and subsumption. But what is interesting is that the type compatibility used in languages sometimes differs from the natural subtyping relation. For example, although it's typically the case that int is a subtype of long, C also allows long values to be implicitly truncated when assigned to an int variable. The designers of C felt that this was convenient, and they wanted to support it, but it can cause errors. To help programmers avoid these errors, Java has a different design. Java type compatibility does not allow assignment from long to int, but if you really want to do it, then you can do it with an explicit conversion. A second key concept is type equivalence. When are two types the same? And there's different rules for handling this. Finally, there's type inference. What is the type of an expression given the types of its operands? We'll study these first two questions in this lecture and go to inference in the next one. There are two notions of type equivalence that are typically used in programming languages. To motivate these, look at the following types. We have a person who has a string name and address, and a school that also has a string name and a string address. Are these the same type? It turns out that some languages let you choose. So for example, in Ada, we can declare a type score that's an integer. And here structural equivalence is used. We say that score is the same as any other integer. We can assign between them. On the other hand, in Ada, we can declare that type Fahrenheit is a new integer type. This stamps a new name, Fahrenheit, on the type and denotes to the compiler that we cannot implicitly convert between Fahrenheit and integers. And so if we also have type Celsius, which is a new integer, we can't assign Fahrenheit to Celsius. And that is good, perhaps, because it could help us avoid conversion errors between units. Name equivalence is based on declarations. You declare a type, and you say whether that it's equivalent to another type, but that it is stamping its own identity onto that type. The advantage of name equivalence is that it captures the programmer's intent well. This is a new type that I want to be distinct from others. Name equivalence is typical in imperative and object-oriented languages. On the other hand, structural equivalence is based on a structural correspondence between the different parts of two declarations. The advantage is it's more flexible. Perhaps we design two types that represent the same thing, but we call them different names. Well, those types will be assignable between each other in a structural type system, so it can be very flexible. A disadvantage, however, is that it can accidentally equate types that we didn't intend to be the same. This is common in functional languages, but functional languages also usually have some way to support nominal equivalence as well. How does structural equivalence actually work? Well, what we do is we compare the type descriptions, and whenever we come to a name, we substitute it out with its definition. And we'll expand all the way until we get to built-in types. This gets a little bit more complicated when we have recursive types. And in fact, recursive types often do not have structural equivalence in practical languages, although there's fairly complicated theoretical approaches for doing so. In this case, the original types are, if we can expand it out, then the original types are equivalent if the expanded type declarations are the same. Let's talk about coercions. When an expression of one type is used in a context where a different type is expected, one normally gets a type error. But consider the following example. We have a variable a of type integer and variables b and c of type real. We're assigning c the value of a plus b. Many languages allow this, and they'll coerce an expression to be of the proper type. In this case, the integer a will be coerced to a real before we add it to b. Coercion can be based on just the types of the operands to some operation, like plus or like a function call, or it can take into account the expected type from the surrounding context. The C language has lots of coercions, but fortunately they have fairly simple rules. All floats in expressions become doubles. Short, int, and char become ints in expressions. And if necessary, we'll remove precision when we assign into a left-hand side that doesn't have the appropriate precision. Now sometimes you need to convert between types, but the language doesn't implement the coercion you want. In these cases, assuming there is a conversion available between those types, you can put in an explicit conversion to make it happen. Here's some code in Java. We're getting the time in milliseconds and putting it into two long values. Then we'll subtract them, and the difference between those two times should fit into the integer range as long as we're not running this program for, a very long period of time. Because Java doesn't allow us to implicitly coerce longs to integers, we have to add a conversion in Java, which takes the form of a cast. Terminologically speaking, type conversions are explicit and written by the programmer. And in C and derived languages, we often use the word cast for those conversions. On the other hand, type coercions are implicit and are inserted by the compiler. We can look at how coercions are inserted into source code using an elaboration procedure. Typically, the elaboration will be a pass within the compiler, and what it does is it makes implicit things explicit. In this case, elaboration is driven by the types that we see, and we add a coercion wherever we need to make types match up, assuming a coercion is defined. So coercions are inserted when subsumption is used, but the types have different representations. For example, there's a subsumption relationship between int and real. We can treat an int as a real, but they have different representations, so we actually have to do something when we make that conversion. The coerce real rule will observe that an expression e has type int, and it will surround it with a float operation, which converts the int to a float, to produce a result of type real. Now, the other way around, there's no conversion, but perhaps the user adds a cast to integer. So the convert int rule will take an expression of type real, and if the user wrote that cast in to integer, then the compiler will insert a truncate expression and so the generated code, which will be on the rough right-hand side of the squiggly arrow in this judgment, basically is more explicit. It calls library functions whenever something needs to be transformed. In this case, that library function might just be a particular instruction in the target machine that converts between integers and floating point numbers. There are various considerations for code generation for both conversions and coercions. If we're converting between types that have the same representation, and the provided type is a subset of the expected type, for example, converting an int to a long in Java, then no code need to be generated because we can just treat the one as the other. On the other hand, a check is generated when the provided type is not a subtype of the expected type. So what if we have an integer and we're converting it to a subrange of 1 to 10? To be safe, we need to check, is that integer really in that range? Some languages skip this check. That's unsafe, but it saves some time and the potential of an error. It just means that the user has to make sure, that the programmer has to make sure they get it right. So conversions from long to int in C or Java would be in this form. C will do that implicitly in a coercion, whereas in Java that would be a conversion put in by the programmer. Conversion code also has to be generated if the types have different representations. So in this case, converting an int to a float requires, again, an instruction that changes the form of the data. Let's check our understanding.